This is what I want to cover today, a lot of important material. Let me start with the bird flu. Just because it's in the news. The chapter, as you will notice, has to do with chain reactions. A chain reaction is a way of turning a small number into a very large number in a relatively short period of time through the doubling rule. First generation, you get 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 10, 28. So you get basically a factor of 1,000 in 10 generations. That's a factor of 1,000. After that 10 generations, go another 10 generations, and each one of those 1,000 atoms will also give you 1,000. So it's another factor of 1,000. So you have 1,000, 1,000. You have, after 20 generations, you have 1,000,000. That's the typical of a chain reaction. And then 1 billion. You know, one more, 10 steps is 1 billion. And then 1 trillion. So it grows really rapidly. Chain reactions occur. You know, this term of a chain reaction has other terms because it happens so much in science, in biology. You'll hear it referred to as exponential growth. The reason it's called exponential growth is if you want to know the number of things you have, the number that you get is equal to, it doubles each time, 2 times 2 times 2 times 2, where this is the number of generations. And so here there are n generations. In this case, n equals 4. Oops, I'm using the same notation. That's no good. Let's call this g for the number of generations. And you can calculate this by saying n equals 2 to the g. That's the math notation for that. So it's called exponential notation. You'll see this in the newspapers once in a while. Things increase exponentially. It's really fast. It happens in many things in our lives. It happens with the fetus when you're conceived and the cells start doubling. How many cells are there in your body? It's about, I looked it up. It's hard to tell. In fact, it's a controversial issue. Nobody really agrees on how many cells there are. Cells are different sizes and so on. But the kind of number I saw when looking up in the biology sites is the number of cells is about 2 to the 11th. I'm sorry, it's 10 to the 11th. So it's 1 with 11 zeros after it. A lot of cells. So how long does it take to get up to 10 to the 11th? Well, we know if you're doubling, and then doubling, and then doubling, you know, we could say that after, you get 10 to the 3, that's 1024, after 10 generations. You get 10 to the 6th after 20. 10 to the 9th after 30. 10 to the 12th after 40 generations. See, every 10 generations, it's a factor of 1,000. So hey, 40 generations. Good. Now, how long does it take a cell to double? Well, you know, biology, you watch a little cell double, and let's say a day. If it takes a day, then you would get to full-size human adult in 40 days. Now, those of you who have had children know it's really 9 months. So what's going on here? Well, the doubling rule doesn't keep up. You can keep on doubling, but you have to get nutrients to all those cells. So it doesn't really work that way, and it slows down just because you have to feed food in. But if it were working, you'd get this. Cancer is an example of a cell that thinks it's a fetus. So you get a little mutation, and this cell says, ooh, I'm a new baby. I want to grow, grow, grow. Double, 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 double. It doesn't take very long before you can have all of your weight in the form of a cancer. And if little pieces break out and they start floating around the body to find better nutrients, and they get stuck in your heart or your brain or your liver or something like that, and you have cancer. And it's this doubling. Doubling, and you got to stop it somehow. But in cancer, your cells, once they reach the size of a baby and you're born, then the cells say, okay, we're slowing down. And eventually, some of the cells actually turn off when you have a fully developed, you know, liver or brain or whatever. The cells say, okay, that's enough, I turn off. So cells are programmed to stop growing once they reach the right size. Most people, experts that I've talked to in the cancer business, believe that what happens with cancer is that every cell has about 4 or 5 different mechanisms for turning off unlimited growth. And they're understanding these now. So they're finding the genes in the cells whose job it is to control growth. And the reason is this is so important to do, that there's this enormous redundancy to prevent the cell from continuing to grow. So in the end, there's something called apoptosis that will actually kill the cell rather than they will find the cells that have not been turned off and kill them rather than let it become a cancer cell. So what people are appreciating now is that for a cancer to grow, you have to have a whole bunch of mutations, anywhere from 3 to 5 or maybe even more. And these mutations then turn off the mechanism that allows unlimited growth. And if you have all these right mutations together, or all these wrong mutations together, then you get the cancer. So biology is looking at now identifying the mutations and seeing what they are, and then addressing them one at a time. And right now, we are probably still near the beginning of an era, in the next 20 years or so. Don't be too surprised if basically cancer is conquered. Because this is what the experts in the field are very optimistic about right now. And the reason they're conquering it is not because they try new experiments and new things, but because they're understanding the mechanisms, because they're mapping the DNA and seeing how that works, and beginning to understand what kind of mutations. What they want to do is when the patient has cancer, is to go in and quickly identify precisely what kind of mutation caused that cancer. And then they might be able to give a particular kind of treatment that's designed for that particular mutation. So that's the future here. Now, I'm talking about bird flu. Another type of exponential growth, doubling law, is a chain reaction, is a virus. Whether it's a computer virus or a disease virus, again, they work the same way. Viruses are very peculiar things. I mean, they really don't satisfy anybody's definition of being alive. In fact, the virus probably never existed until the cell was created, and we had the cell mechanism, which enables a rather complex system inside of a case that has a complex metabolic processes. It's like having a computer. There was no computer viruses before you had a computer. And then you have a computer, and suddenly there are viruses that operate on it. Computer viruses did not exist in the last, in the 1800s. You had to have the computer first. Well, once you have the cell, then a virus is a particular combination of DNA that takes advantage of the cell so that when it gets into the cell is tricked into duplicating the virus. And then the virus gets out. It can't live on its own. It doesn't even live. It doesn't have much of a life. It just sort of sits there as one segment of typically of RNA. And when it gets into the cell, it duplicates, and then the cell dies, the thing breaks out, and then it goes maybe spreading somehow. How does it get to a nearby cell? Within the body, that's not hard. But suppose you kill all the cells in the body, then the thing dies. Then what? How does it get to the next animal? Actually, that's a tricky problem. And so the viruses that wind up killing their hosts wind up not being much of a threat to humans. I get my virus, I'm dead, that's it. So those viruses don't last long. The ones that last long are the ones where they keep me feeling healthy enough so that I will come and meet you and we will cough in each other's faces and we'll spread. And those are the viruses that are really successful. And if they're going to kill you, make sure you don't do it too fast. Give time to spread. Right now, there's a virus going around called the bird flu. And the way it works now is it's spreading among birds. I was going to look up how it spreads among birds. Does anybody here know how it spreads from one bird to another? I'm not sure how it happens, but it does. And so it's spreading around the world, and almost every day there's bird flu found in Denmark, bird flu found in Nigeria, bird flu found somewhere else. And it's being spread by birds, by migrating birds who don't die, because if they died, they wouldn't migrate. They get sick and they die slowly, maybe, but they they have to reach other birds. Now, if you come in contact with an infected bird, you can get the virus from the bird, and then you have a 50% chance of dying from it. So far, that's how people die from it. This is why they're so afraid of it. So you get this bird flu, and you walk around and you cough in someone else's face, and they don't get it. The status of the bird flu right now is you get the bird flu, you go around coughing in people's face, you know, shake their hands, you do whatever you do with other people, and they don't get the flu. Oh, so it's not spreading exponentially. No, it's just spreading by contact with birds, especially people who live in farms. So what's the big fear? Well, it's spreading exponentially among the birds. Can we stop that somehow? You know, it seems almost hopeless to stop the spread of bird flu. You hope that, I mean, it's going to spread and spread and spread and spread. You want to minimize contact with humans because it kills humans when it jumps to the human, but it doesn't spread exponentially among the humans. So what's the worry? Well, at some point, you think the bird flu will eventually die out. You know, it'll spread. The birds will get their immunity. This may take years. And then eventually bird flu won't be a problem anymore. But what people worry about is that it will spread to some human, and then viruses mutate. They're always changing. And if it mutates in such a way that one human can spread it to another, now you have the possibility for a chain reaction among humans. And chain reactions among humans are much worse than they have been in any other time in history because we travel so much. You know, the bird flu breaks out in Korea, let's say 2 weeks ago. You can ask yourself, how many people who were in Korea 2 weeks ago are now in the United States? And the answer will be thousands. So that kind of spreading, that's, in biology they call that a vector, a way of transmitting disease. And now because of travel, things travel around, viruses can travel around the world much faster, so that is the worry with bird flu. It is not yet spreading exponentially, no chain reaction among people, but with a mutation, it's so deadly that if it does come up with a variation that can spread among people, then that could spread very, very rapidly. You know, if something like that here starts in Berkeley, expect for there to be a quarantine of Berkeley, where people won't be allowed to leave Berkeley, or any other city where this happens, because that's how dangerous this is. So this is why people are so afraid of the bird flu. Anything that kills that, there was this flu in 1918 that killed more people than World War I. In fact, some people believe that World War I ended not because of the armies, but because the bird flu basically killed off the armies. Not the bird flu, back then it was a version of the swine flu, but it's related to this one. It's called H5N1, having to do with the surface of the antigens on the surface of the flu virus. So that's the story in bird flu. We discussed cancer. Computer viruses are the same way. What are they? They're a little bit of code, which if you get into your computer, spreads the code to another computer. And then it's not just a chain reaction, because you don't necessarily spread it to just 2 others. You could spread it to 10 others. And if you spread it to 10 others, then they spread it to 10, to 10, to 10. You have 1 billion computers in just 9 generations. 10 times 10 times 10 times 10, 10, 10, 10, 10, 10, 10. Oops, I had the extra one, sorry. So 10 generations, it can spread to every computer on the world, assuming that they're all in contact with each other. That's why people worry about the internet. It's a great vector for spreading. The thing that amazes me about the computer virus is that it is so much like a disease virus. I mean, it's really just a little bit of code. And now the problem is once you start killing, once you, in your body, you start having all these viruses being come out, your cell really usually cannot survive because it's spending all of its food energy creating new viruses. And so you wind up getting sick or dying. Meanwhile, your body is designed to fight these viruses. It identifies things that are alien, sends around white blood cells, pumps in chemicals, sends around white blood cells, even heats you up a little bit. It's called a fever to try to kill these things off. But a computer virus is so similar. It's just a code. It's just a few lines of code. That's all a virus is. It's not a physical thing. It's something that can be sent electronically. Really a remarkable analogy there. Chain reactions. Not all viruses, by the way, not all diseases are viruses. Some are bacterial. Others, like anthrax, are little spores that will, when they get into your body, will will grow. They're like little cells. They produce toxins. And if you get infected with anthrax, perhaps by breathing in these spores, then you have anthrax. And what is the danger you'll spread it to anybody else? Essentially zero. Anthrax doesn't spread from person to person. That's one of the reasons why people talk about using, bad people talk about using anthrax for biological warfare. Because you spread anthrax. Shiriki, the Japanese cult, tried to do that. They tried to spread anthrax. They wound up spreading anthrax. It turned out to be a non-dangerous variety. They got the wrong anthrax. But they tried spreading it over Tokyo from the roofs of buildings. The idea is anthrax will kill you. But typically anthrax spreads when an animal gets anthrax, dies, the body gets completely infected with anthrax, the body rots out in the open, the anthrax spreads out over the grasses and so on into the air, and then you breathe it. Human culture has developed a procedure of burying its dead, and whether this has religious origins because God dictated this, or a biological origin, certainly makes biological sense. Which if you bury the dead, the disease, the things that invade the body and grow will not spread if you put them underground. Let the bacteria happen. So not all diseases spread that way. And I'd like you to understand which things spread that way and which things don't. Anthrax doesn't spread that way. For a long time, it was believed that human population is basically a disease on the surface of the earth. Some of you may still feel this way. That here we have this nice, pleasant earth with green and so on, and these humans get in there and they start doubling and doubling and doubling and doubling. It's a population bomb. That was a term that was popularized in the 1960s by a scientist, a chemist at Stanford named Paul Ehrlich, who's become somewhat of a national hero on spreading this. But it really goes back to Malthus. A link to a Malthus essay I put on the website with the population explosion. The problem is simply that two people tend to have more than 2 children. And if there's plenty of food for the 2 children, then maybe you'll have 4 children, right? And then that's a doubling of every generation. And in the next generation, and here's where the word generation comes from, you'll have doubling the first generation and doubling again, doubling again, doubling again. You plot it, it goes boom. And pretty soon you run out of resources. Now what happens if you have 4 children, but there's only the same amount of resources? Then half of them are going to die. So Malthus pointed out this doubling rule. The danger that in human population we would outgrow the resources, then there would be starvation. And some of other philosophers back at the time of Malthus, I think he was, 1700s, Malthus, looked at this and said, see, we should not try to eliminate starvation. Starvation is absolutely necessary in the world as a way of maintaining the population. And that's what led to the term that economics is called the dismal science. It really came out of, not Malthus, but the people who expanded on Malthus and said, we got to just let them die. And this philosophy was actually used when there's a potato famine in Ireland. There were people saying, we shouldn't even try to do anything about it. This is a result of the population explosion. Later by Ehrlich, called the population bomb, in analogy to the atomic bomb, which it is analogous to. It's doubling. We had an example of this with rabbits in the 1800s. An enterprising rancher brought some rabbits to Australia, let them loose on his ranch. I think he brought 12 breeding pairs. Now, the rabbits had no natural enemies. There seemed to be a lot of food around. They had this whole continent of Australia, which had never had rabbits before, because it's isolated as an island. No enemies and lots of food. So they started doubling. And 3 years later, he reported he started making his money by having rabbit hunting on his ranch. Come and shoot rabbits. And bang, bang, bang. And 3 years later, I think the number was that he reported that hunters who came had killed 3 million rabbits on his ranch. Of course, rabbits spread all over Australia, and they are a major pest in Australia. And it happened exponentially. Within a few decades, rabbits were everywhere in Australia. You will still hear the term, they breed like rabbits. And that goes back to the 1800s when this actually happened. And the story, of course, was international news about what had happened. People became aware of the problem of breeding like rabbits. So people worry about humans breeding like rabbits. Interesting thing, though, and this is something that is important for you to know. I give some references in the textbook, and that is that humans are no longer breeding like rabbits. And nobody really understands why. You look at the population growth over the history of time, you see exponential growth tends to go like this. And human population as a function of time, there's a war and it goes down a little bit. Then there's some abundant thing. And so there are variations like this. And it's been going like this. And now it seems to be turning over. The best data is that it's turning over. In fact, this is no longer controversial. I'm not telling you something that anybody who is knowledgeable on the subject disputes. They may not understand it, but they don't dispute it. There you will find most of the people you know are unaware of this fact, that it's turning over. They still remember things that they learned when they were kids growing up. And the fact that the population has left the exponential curve is the big surprise. Right now, if you look at not only there is an article, I give a reference to it, and I think it was in Physical Review Letters, there is official United Nations reports that the population now is no longer expected by anybody who's an expert in the field to keep on growing. But sometime around 2050 or so, we'll probably reach a maximum. People don't know whether it's 9 billion or 12 billion. Probably closer to 9 billion. And then it will start to go down, possibly. We have left the exponential curve. Now, back in 1960, Paul Ehrlich was talking about the great mass starvation that there would be in by 1970 in his first book, The Population Bomb. Subsequent to that, he predicted 1980 and then 1990. His speeches are still very popular. He can go around scaring people, and people get scared. But it turns out to be not true. So what's going on here? Basic answer is we don't know. Now, off my subject of expertise, and I will put on my non-expert hat and tell you what I find, I hope that the answer is. So this isn't physics. This is speculation. It's a popular speculation among the people who are experts in this field. But it's the most optimistic. And that is, the standard of living of the world is going up. We really are getting rid of a lot of disease. I mean, there's a terrible tragedy happening in Africa right now with AIDS. But most of the classic diseases, AIDS is killing so many people that you're not having a population growth there. But in the rest of the world, it's not disease. What seems to be happening is it's improved standard of living. And so here's the guess. And again, I'm not speaking as an expert here, but the guess is that when people know that their children are going to survive, then instead of trying to have a large number of children in the hopes that a few will survive, you have only a few children and you nurture them extra well so they can live well. If that's what's going on, then we're having a very optimistic future. Right now, population of the world is about 6 billion. I think that's, so it's going to go up quite a bit. The other thing that people worry about is that as we get up here, if this is happening because people's lives are improving, then people's lives maybe will continue to improve. Imagine everybody in China, every individual in China, living at your standard of living. Isn't that a wonderful future to think about? Other people shudder because they say, we are using so much of the natural resources of the world that if you take a population of 1 billion people in China and have them live at the standard of living of the US or Europe, that the number, and then do that for India also, that we will simply gobble up the natural resources, produce carbon dioxide, pollute the world. What an awful future that is. I have one expert friend, and he is a real expert, Art Rosenfeld. He's now California Energy Commissioner. He's still an emeritus professor here in the physics department. And what he points out is that one could live at this level, same level that we're having now, and with the right kind of energy efficiency and conservation, we could actually have the world using less resources than we're using today, with a population of 12 billion, with everybody living at our standard of living. So the future is not bleak, provided that we learn good energy efficiency and conservation things. And that's a fascinating subject about which I do know a lot, but which I'm not going to dwell on right now because we're into exponents and rabbits. While we're into rabbits, let's talk about O.J. Simpson. O.J., I remember the trial rather vividly. There was evidence that indicated that he had some of the blood on his hands from the murder. The evidence had to do with a new technology called DNA, basically DNA identification, DNA ID. It used a technology called PCR. Identifying DNA has become an industry of its own. It is based on the technology that Kary Mullis invented called PCR, and these are two things you really need to know. Now, here's the problem. DNA is unique to every individual. There are certain parts that we have in common, like the same DNA that tells our heart how to pump blood. But there's a large fraction of the DNA that seems to be random, and each one of us is sort of different there. As near as we can tell, this DNA doesn't do anything, although I wouldn't be too surprised if we find out 10 years from now that this DNA that appears to do nothing is actually doing something. But it is different in different individuals. Now, that means if you could get a hold, let's say someone leaves a little bit of DNA behind in a crime scene. Sometimes it's their own blood, sometimes a little bit of skin, sometimes it's just the hair, although the hair has to include the follicle of the hair because that's the only place where the DNA is, down here in the follicle of the hair. But these are frequently found at a crime scene, especially a violent crime scene where people fight. You find this evidence. Fingerprints may actually leave a little bit of DNA behind. DNA, deoxyribonucleic acid, being the molecule within the body that contains the code. It's the molecule that tells the cell how to do things. And each of our DNAs is a little bit different. Of course, you inherit your DNA from your parents, so half of your DNA matches that of your one parent, the other half matches it of the other parent. It's sort of mixed together in a random way, but you don't have your own DNA. For the most part, you are the DNA of your parents, half of each. That means that if I would like to know, for example, whether my father is really my father, all I have to do is look at his DNA and look at my DNA and see if there's the expected match. If he really is my father, then there's a lot of overlap. About half of it will be the same. What they actually do is they find little segments to compare. So these days, paternity is no longer an issue. There is a measurement that can be made, and the price is going down every year, to check this sort of thing. It's really interesting. It has deep sociological consequences. The most famous case, now O.J. Simpson, the DNA evidence, was ignored by the jury. The reason they ignored it was that the defense attorney pointed out that although the DNA evidence shows he was there, or rather the DNA evidence, now I forget whether it was he had blood on him or whether the blood was found at the site from him or what, but the DNA evidence linked him to the crime, assuming that the police had not decided to go out and get O.J. Simpson by purposely leaving some of his blood at the wrong place. And that's what couldn't be excluded. It was the fact that the police, now, you know, some people absolutely trust the Los Angeles police. They would never do anything like this. Other people are very suspicious of the Los Angeles police, and they think, boy, they would really like to go out and get this guy. So it was based on that, on the handling of the DNA, that this evidence was basically excluded, and O.J. Simpson was pronounced not guilty. A more fascinating case in my mind is the case of Sally Hemings, who was the slave of Thomas Jefferson, and who told her children that their father was Thomas Jefferson, although Thomas Jefferson never acknowledged this. And then the children had children. It was passed down many, 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 many generations. And now we have the descendants of Sally Hemings who claim they are descended from the President Thomas Jefferson. 200 years have passed. Back in those days, it was a scandal. You know, it was a scandal like Watergate, or like this question of these children and so on. Of course, nobody could tell for sure. Now we have the descendants. But you see, every time you have a descendant, you pass on half the DNA. What that means is some of the descendants should have actually a fair fraction of their DNA that's identical to Thomas Jefferson's, even though it's been cut in half many, many generations. Suppose it's 25 years per generation, it would be about 8 generations. So it would be cut down by a factor of 2 to the 8th. 2 to the 10th is 1,000. This would be down by a factor of 256. You still have some DNA from Thomas Jefferson there. Yeah, but you don't have Thomas Jefferson's DNA. What do you want to do, go exhume his body? No, but Thomas Jefferson did have other children. And so you could look at Thomas Jefferson's children, the ones that he had with his first wife, and you could look at his only wife. He never married Sally. You look at their children, and here you have Thomas Jefferson and Sally Hemings. And you look at Sally Hemings' children, and you look at Thomas Jefferson's children, and they should be this still has some of Thomas Jefferson. The question is, do these people have any of Thomas Jefferson in them? So that study was done, and you expect it to be greatly diluted, maybe by a factor of 1 million, but you expect more of an overlap than you would from random people, and they found the overlap. They found the expected overlap. So the conclusion is that, yes, the descendants of Sally Hemings were actually also descendants of Thomas Jefferson. Who would have imagined 200 years ago that people would be able to figure this out 200 years in the future? This is one of the most marvelous things, I think, in science. What's more marvelous is the following. I have 2 daughters. And in the olden days, women had to be very careful about getting pregnant, because the man would always deny, oh, it's not mine. And then the woman would have to raise the children or do something somehow. And the man could be said, you know, he would walk away. So men could basically have a great deal of sexual freedom, and the women would have to be very super careful. Well, that's all changed now. Now it's the men who have to be super careful. Why is that? Well, you have some casual sex with some woman that you find attractive but don't really like. And that woman has some babies, and guess what? You have to support that woman and her babies for the rest of your life. How can she prove that you're the father? Well, that's easy. Use a DNA identification. As the father of 2 daughters, I am really delighted in this change of responsibility. So little things like DNA identification can have major changes in the way people run their lives. So be careful, you guys out there. Now, where was I going with that? Oh, I haven't explained what PCR is, because PCR is the thing that makes the DNA identification possible. Here's the way it works. Suppose you get 1 molecule of DNA. You'd love to look at it with a microscope, a super microscope, and read the sequence out. And if you could do that, you wouldn't need anything else. But we can't do that. We don't have the technology for doing that. Hasn't been invented yet. We cannot see a particular molecule down at that level and read out its molecules without destroying it. So this is where Kary Mullis came up with this very, well, you got a Nobel Prize for it. And the idea is, hey, DNA is different from everything else. DNA is designed to replicate. You get one molecule of DNA within the body, it splits, you wind up getting two cells, 4, 6, that's, that's the growth of the fetus. So DNA is designed to replicate. Let's help it along. Suppose we have a blood sample or some hair or something like that, or maybe a sample from a rape. This is, you could really tell. Rape these days, and again, from the point of view of a father, you can find out who did it without doubt by matching the DNA. So you get some samples, and you get, but you don't have very much. And so you can't measure it because you don't have the super microscope. That maybe somebody will invent someday. What you need is, if you want to analyze the sequence of DNA, there are many ways to do it, but you require having billions and billions of molecules. So that what you do is you take billions of molecules, and on this one you measure a little bit of this piece, and this one this piece, and this one this piece. You can put the whole thing together. People can do this now. But you need billions of copies, trillions of copies. So what Kary Mullis did is figured out, hey, look, this is sort of obvious, right? DNA, it's designed to replicate. Let's use the chain reaction. So it came up with a method where you first separate out the little piece of DNA that you want by using a couple of cutting enzymes. The details of this you don't have to know. Then he would mark them in a certain way, and then if you put them in the right fluid, they would replicate. And the trick here was a kind of temperature cycling, where you heat things up so they replicate, and then you cool them down, heat them up, they replicate again, and so on. You get the cycle going. And it was called a polymerase chain reaction. The polymerase were the enzymes. Polymerase, P-O-L-Y-M-E-R-A-S-E, polymerase chain reaction. The polymerases were the material that would get this chain reaction going. And so with a tiny little sample, like one hair if it had the follicle on it, they could now amplify this. Amplify it meaning chain reaction, double it, double it, double it. It takes about half an hour until you have enough material so that now you can actually analyze the DNA. And this means if you, I had a friend once who did this to me. He said, Rich, congratulations. He held out his hand. I didn't know what he's congratulating me for. And I shook his hand, a little bit sticky. I said, what are you congratulating me for? He said, well, I've just obtained a sample of your DNA. He had a little Scotch tape on his hand. And he was just shaking it, getting my DNA. He said, now I have your ID. I can find out where you've been, what you do. And people are talking about DNA identification at airports. Cannot be done yet because it takes anywhere from a half hour to several hours to do the whole thing. So it's not a real quick ID, but it's a real ID. You use the PCR, this chemical cycle. And some of you may work in biology labs in which you do this. PCR, remember that, PCR. Polymerase chain reactions. CR stands for chain reaction. It's a way of multiplying up the amount of DNA so that you can do identifications. And it is proving enormously important. It first hit the news with the O.J. Simpson case and Sally Hemings, but when they were identifying remains from the World Trade Center, that's how they did it. They would get little pieces of the body and use the PCR and compare it to the DNA of close relatives. This is how they could just find out who was actually killed in the World Trade Center. They do this with catastrophes all over the world now. One of the most interesting examples, though, is in examining people who are convicted of crimes. Sometimes, in certain cases where a crime has been committed, there was some evidence. For example, a blood sample was taken. There was some blood at the scene which didn't belong to the victim. And they matched the blood type. This is the old way of doing it, blood type. Is it a negative blood type? Is it a B positive? They have about these 7 categories of blood types, and they would compare it. And if it was the same blood type, they'd say, gee, 1 chance in 7 that this is the right, this is evidence to help support the case that this person was guilty. Now, in some of these cases, they kept the blood samples over the decades. And now that we have PCR and the DNA, it's called DNA fingerprinting, it's not really fingerprinting, although when I shook hands with my friends in a Scotch tape, that might have been considered fingerprinting. Fingerprinting is just because that's the term that that's how people used to identify people from their fingerprints. Because we all have different fingerprints. Even identical twins have different fingerprints. This is called DNA fingerprinting because it does the same job. And now, in some of these cases, they have gone back to where the evidence was preserved, and they have the old blood sample. And yes, it's A positive, and the man who was convicted had A positive. But does the DNA really match? So now they can actually take a sample of his DNA, a sample of that, and in many cases, it really does match. This is a much better thing. This is the sort of thing where the odds of it happening by chance are so great that if you measured everybody on the earth, you'd get only one match. And there are a few cases where it doesn't match. And the blood at the scene of the crime is definitely shown to have not come from the person who's been in jail. In many cases, you can read about this, it happens every few weeks, you see something else. There are students who, as class projects in the School of Law, go and find people where they think the evidence wasn't really very strong, and where there is some DNA evidence that can be tested, and they go and they see to it that it's being tested. Now there are people are seriously looking at laws where every single case where someone is in jail and there is evidence that can be analyzed with DNA, that there should be funds to do that, because a large number of people are being found not guilty who have spent a long time in jail. It was so bad that the governor of Illinois decided that they would have no more executions in Illinois. There are just too many of these cases in which the DNA evidence was proving that the trial system is not working as well as we had hoped it works. So this is in a sense a test of our trial system and how well, when we convict somebody and put them in jail, maybe on death row, how often does it make a mistake? I haven't seen the numbers analyzed for that, but I think the number is much larger than any of us would really be comfortable with. So that's the story of DNA fingerprinting and polymerase chain reactions. Getting back to nukes now. Gabon. The French were mining uranium there, and they were pulling out uranium, and uranium is 0.7%, uranium-235. And that's what they were extracting. They brought some of the uranium from Gabon to their laboratories, and they discovered, to their shock, it was less than 0.7%. At first, this was immediately classified, a panic. Somebody was stealing the uranium-235 out of the ore. Well, yeah, I mean, you think about that, you realize that makes no sense. It's extremely difficult to extract out the uranium-235. You do that by purifying it and running it through your calutron or running it through your centrifuge or something like that. So what's going on here? The French finally figured it out. And it became one of the most fascinating stories of a few decades ago. The uranium in Gabon, Africa. Gabon is a small country just south of Nigeria on the west coast of Africa. I'm sure you all knew that. Gabon, the nuclear, what had happened was the uranium was very concentrated. Now, you have pure uranium there, pure uranium ore, uranium oxide. You can't get a chain reaction going, right? Because it's only 0.7%. And to get a chain reaction going, even if you had a moderator, which would be water, you could get water. You could imagine rain coming down into the uranium and being around the uranium in such a way that maybe you get a nuclear reactor going. Except you only have 0.7%. At 0.7%, there's no way. As we explained, you have to enrich the uranium. Well, you could do it if you had heavy water. Remember that? The Canadians have a CANDU reactor, it's called, and they use heavy water, and then you could use unenriched uranium. But there's not heavy water flowing out of the sky. The French concluded that at Gabon, there had been a nuclear reactor, a natural nuclear reactor underground. and that a chain reaction had started, giving off heat, and there had been enough of a chain reaction that some of the uranium-235 was used up, and that's why they had depleted uranium coming out. But how? How can you have 3%? That's what you need. In our nuclear reactors, you can have water as a moderator with about 3% uranium-235. The answer turns out to be amazingly simple. Go back in time. The uranium itself has a half-life of about 1 billion years. It's actually 0.7 billion years, 700 million years. If you go back 700 million years, you had twice as much uranium-235. Well, 0.7% becomes 1.4%. Go back another 0.7 billion years. And instead of 1.4%, you have 2.8%. See, the uranium-238 has a much longer half-life, so it doesn't change that much. But the uranium-235 does. So if you work out the numbers, you can go back 1.7 billion years ago. This is before there was any life on Earth. 1.7 billion years ago, there would have been over 3% of uranium-235 at Gabon. And the uranium was in such a concentrated area that the calculations show that you would get, with water seeping in, you could get a chain reaction going. You have a nuclear reactor underground in Gabon, Africa, giving off heat. Well, if that's true, what kind of evidence could you come up with? Well, one possibility is if you have fission going, then you're going to create fission fragments. Some of those fission fragments will have half-lives that are short. They'll decay to other things. But you can predict. You look at the waste that you get from a nuclear reactor, and you find these are the fission fragments you get, and after 1.7 billion years, what will be left? There'll be a certain distribution of fission fragments and decayed fission fragments. So they did the analysis, and they found just what they expected. So this is a verification that in Gabon, Africa, there had been a nuclear reactor 1.7 billion years ago. A rather amazing story. Another neat thing about it is, okay, so you had a reactor underground. That's dangerous. After all, what if you get a meltdown? If you get a meltdown, then the radioactivity from the stuff gets into the ground and can spread out. And what happens with groundwater? Do these fission fragments drift? Do they travel thousands of miles? So they were able to measure that too at Gabon. They had 1.7 billion years to spread. They found most of the fission. They basically found all the fission fragments that they expected to find still within the vicinity, the immediate vicinity of Gabon. It had not spread. So at least in that one case, the radioactivity did not spread far. That does not mean that you don't have to worry about radioactivity that gets into the ground if we have a nuclear meltdown. It just means in the one case where it happened, it didn't spread. So that's the amazing story of Gabon. Well, I should add in here cold fusion. Today is full of anecdotes, each one of which you want to know, each one of which is relevant to future decisions about nukes, about energy, about guilt and innocent. When the governor of Illinois, let me give an example. When the governor of Illinois announced that he was commuting the sentences of everyone on death row in Illinois because the DNA evidence is showing they made lots of mistakes, and therefore he didn't want to execute innocent people, the former governor of Texas, now our president, George Bush, was asked, will he do a similar thing in Texas? I guess he was still governor of Texas at the time. This must have been during the campaign. Would he do a similar thing in Texas? And his answer was, no, in Texas we have not made those kind of mistakes. We're much more careful with our criminal system. I don't believe they had done any of the DNA testing. But you can see how this becomes a political and an important issue at the top levels of the U.S. government to understand these things. So let me talk a little bit more about waste. Getting back to Yucca Mountain. You got to know that Yucca Mountain is the waste facility. You saw it in the film. We're going to see if we can get that film such that you can see it again sometime in the future. We won't be able to do that before the exam. For those of you who missed it, I don't believe there's anything new in that film that we haven't covered in either the lecture or the book. If there was, let me know and I'll point it out to everybody. Nothing new that will be on the exam. We have this facility in Nevada where we're going to store the nuclear waste, and people worry about whether we can keep it safe until it has decayed away to the level at which it's completely harmless. And there's an interesting sociological issue here that I'd like to point out. And that is, I wound up writing an article on this. If you want to read my article, not required, you go to my main web page, and I wrote a series of articles for Technology Review. One of them was called The Witch of Yucca Mountain. And that's on my main web page. I had that published in Technology Review, analyzing the public fear of the radioactivity from Yucca Mountain. And I do a lot of calculations. One of them is to calculate what would happen if 1 year from now, all of the waste from Yucca Mountain basically somehow gets into the soil and starts spreading. In other words, the containment truly fails. Nobody can imagine any way this can happen because the waste is put in these little capsules that are completely impervious to rain and earthquakes and everything else. So nobody has imagined how this could happen, but suppose it got into the soil. And as a comparison, I talk about a large amount of uranium that is currently well mixed with water. And that water, mixed with this uranium, and we're talking here about 20 times more than at Yucca Mountain, 20 times more radioactivity than at Yucca Mountain. The water mixed with this is used for the population of San Diego and Los Angeles. Right now, 20 times more radioactivity. The water is well mixed with the uranium of a form that dissolves in water, by the way, not like these little capsules. And this water is then sent down to Los Angeles. What I'm referring to, of course, is the Colorado River. The Colorado River comes from Colorado. Colorado are these granite mountains. Granite mountains are several parts per million uranium. It's spread throughout the mountains. The water comes down, seeping through in intimate contact with this uranium, and then it comes down into the Colorado River where the water is drunk. And this has 20 times more radioactivity than if Yucca Mountain were completely disintegrated and all the water got in. Yeah, but wouldn't it kill more people if it were Yucca Mountain than if it were Colorado River? Not according to the linear hypothesis. Linear hypothesis which says these very low levels are dangerous. If the water gets into the population, it's simply the amount of radioactivity that comes in. And so Yucca Mountain, I believe, is demonstrably safer than the water system of Los Angeles, even if all of the radioactivity leaked out. And of course, nobody expects it to. So it's a paradox there. In fact, I was thinking about this, and there's some numbers I want to look up. What is the current level of radioactivity in the Chernobyl region that has been evacuated? I don't know the number, but I believe it's very low, but measurable. How does it compare to the radioactivity of Denver? Denver has a large amount of granite. Because of that, there's a lot of radon seeping out of the ground. And it's you get about 50% more, you get about 100 milligram a year from Denver. Imagine the following. This is something that I have a problem with because I don't know how to handle this paradox. Imagine that Denver didn't have that upper level. Suppose it was just the same as at Berkeley. And there was a reactor accident in Denver, and the level went up to where it is now. Would we evacuate Denver because there was 100 milligram per year? 100 milligram per year is 0.1 rem. One cancer is 2,500 rem. So that means the chance of getting cancer per year if you're there, is 1 over 25,000. Well, gee, if you have, I don't know how many people live in that area, let's say a few million, let's say 1 million, and you have 25,000. So basically you should get, if I did this right, about 40 per year in Denver. 40 extra people dying of cancer every year. 10 years, that's 400. So should we evacuate Denver? Well, hey, people have been living in Denver for 100 years, and their cancer rate is lower. These are the sort of paradoxes. How do you handle this? If you're the president of the Soviet Union, well, what used to be in the Soviet Union, Ukraine, and you have the Chernobyl accident, do you evacuate the entire region when it's demonstrably safer than Denver? I'm not giving you the answer here. I'm simply saying the answers are not so easy. And it helps to know the arguments on both sides so that when you see someone defending one point of view, you don't think that they're a cruel, inhumane person or mean or stupid. That these are issues, I mentioned before, that in our society we tend to give a lot more attention, a lot more national energy to the possibility that a few people will die in a mining accident because of the fact that they're trapped than we do to the 40,000 people who are killed every year in automobile accidents, because it's not quite so dramatic. So as a society, we don't measure all deaths equally. I might ask you, how much money would you be willing to donate if it would save a human life? You know, today, here, now. Out of your pocket. Well, best guess is that you could save a human life for somewhere between $5 and $10 if you were willing to give the money. Best place to send it would be to some of the people in Africa who are trying to, probably, you know, I don't know whether it's tuberculosis or simply polio. But you can save money, really, you can save lives right now, today. If you don't do that, does that mean that you don't value a random human life at the level of $10? Think about it. It's not obvious to me what it means. I think as a society we do tend to discount random human lives and not count them very much. Whereas if this particular person will spend $1 million to save their life. But a random life, if you could save one life somewhere in the world, $10 out of your pocket. So these are things that physicists don't have answers to. But they become issues when we talk about nuclear reactors and waste storage and things like that. So that's the story on nuclear waste. Well, we're talking about such fun things. Let's talk about dirty bombs. They're in the news too. What is a dirty bomb? Well, people say a terrorist might come and take a container of highly radioactive waste. Where does he get this? Well, he can get it from a nuclear waste storage site. Well, that's hard. But maybe he gets it from a hospital. It turns out hospitals dispose of a lot of nuclear waste. They use it for radiation treatment. They use it for radiation imaging, something we'll talk about when we get to invisible light, for things like PET scans and CAT scans of the human body. They generate this kind of radioactivity. They use it to trace things in the body. So, in fact, there was a famous incident that took place in Brazil where some of this waste was left in a vacant lot, and several people died of radiation illness after bringing it home to show their people this neat stuff that glows and is dark and is hot. So there are these horror stories. So suppose a terrorist were to take advantage of this. Suppose he gets some of this radioactivity, and evidence is there is a place where he could probably get it. In fact, Jose Padilla was supposed to do that. He was going to have a radiological weapon. This was the Chicago street thug who was trained by Al-Qaeda, came to the U.S., was going to do a radiological weapon. So what could you do? Well, you can get this stuff. Now, of course, it's pretty dangerous. Suppose you get stuff where you have, here you have a container, and it's hard to handle because you'll kill yourself. So, you know, suppose you had a container that would give you, let's say, well, you know that a few sieverts can make you sick. 10 sieverts will probably kill you within a few hours. So let's say 10 sieverts per hour. So this is enough to really kill people. You got to get it there. Which means you have to put it in a thick lead container so you don't get the 10 sieverts. And that winds up weighing several, probably 500 pounds. So it's not that easy to transport. Now you take these 10 sieverts and you blow them up in the middle of the city. Spread them out. Well, the problem is here. You have 10 sieverts here. Suppose you spread it out by a factor of 10, which means to cover this table. And you only spread it out in one direction. Then someone standing up to that, because it's spread out, won't be getting much radiation from there. He'll only get 1 sievert per hour. He won't even get radiation illness after an hour. Spread it out a little bit more, and he could be there for days and not get radiation illness. So here's the catch. If you have an intensely radioactive source, but then spread it out, according to the linear hypothesis, you'll get lots of cancers. But you won't get any radiation illness. You won't get any dead bodies. Sometime in the distant future, there will be these cancers. You can calculate that on a pencil and paper. You'll never see the dead bodies because the statistics are such that they'll be hidden by ordinary cancer. So a radiological weapon, a dirty bomb, would I use that if I wanted to have my follow-up to 9/11? Well, maybe yes, because people are so afraid of radioactivity. After all, it'd be like Chernobyl, right? If I spread this radioactivity out, people would abandon the inner city because of the radioactivity. So it has the possibility of spreading fear, but there wouldn't be any dead bodies. Once you've spread it out, then you're below the threshold for radiation illness, and all you say is, you know, here I am, Osama bin Laden, and say, ha ha, yes, these Americans will have an increased number of cancers in the next 30 years. It won't be measurable, but they'll be there, and they are individuals, and they will die. And you really have to ask yourself, is that what Osama bin Laden will do for his next terrorist attack? Well, personally, I think he's dead, so I don't think he's going to do anything, but let's say Al-Qaeda. That's the problem with a radiological weapon. Once you spread it out, you get below the threshold with no radiation illness. The only thing you get is cancer. It doesn't produce dead bodies once you spread it out. In Brazil, it wasn't spread out. That people took pieces of it home to show their kids. And there were people who died of radiation illness. But if you spread it out over a city, pretty soon the effects become ones you calculate, and you're depending on fear, not on dead bodies. There would not be dead bodies to show on TV. My own evaluation is that if I were Osama bin Laden, that would not be a good follow-on for the buildings falling down and the Pentagon being blown up. That I'd want something more dramatic. But I may be wrong. I don't really understand Osama bin Laden that well. Now, and not only that, but Al-Qaeda, Jose Padilla, who was supposed to come to the U.S. and do a radiological weapon, got, according to his trial, he was notified by Al-Qaeda to give up the radiological weapon thing. He was told instead what he should do as one person by himself. What can you do? He can't hijack an airplane. He came here. One person was going to do the radiological weapon. They decided that was not a good thing to do. This scares me because it means Al-Qaeda knows as much about this as I do. Instead, they told him what he should do is rent some apartments in different apartment buildings, ones that use natural gas. He should leave the natural gas turned on and have some sort of a spark mechanism that would cause the apartment buildings to burn down simultaneously from a natural gas explosion. Now, here's what scares me, okay? They were right. Having explosions in apartment houses simultaneously spread across the city of Chicago, I fear would really spread terror. Would they make everybody worrying about their neighbors? Would make people very suspicious? Would cause deaths if done at night? Could be really horrible. The radiological weapon, which is the one that's getting all the attention, to me would just fizzle out. And most people would say, oh, there's radioactivity there. Don't spend more than 6 hours downtown for the next few weeks until we wipe it up. Would that spread terror? I fear that within the U.S., we are not fearing the right kind of terrorist attack because of our exaggerated fear of radioactivity. So this is where it becomes an issue. And when you guys are presidents or congressmen and so on, I expect you will know that, as you will know it, for midterm or final exam. So that's the dirty bomb. Now let's talk about fusion. Fusion gets in the news quite a bit. People talk about it as the energy source of the future. Fusion is the process that takes place in the sun that gives us basically all of our clean energy here on the Earth from sunlight. Basically, all of our energy ultimately comes from sunlight because it's the sunlight that provides the energy for the creation of carbohydrates, which go to our fossil fuels. Now, in the sun, the process that takes place, in the textbook, I have an optional section, which you're welcome to skip, that talks about the nuclear reactions that take place within the sun. But in the end, you start with 4 hydrogen atoms. You wind up with 1 helium and a bunch of little pieces. And that's what happens. This is why it's called fusion, because you start with light things like hydrogen, you wind up with 1 heavy thing, helium. Helium weighs 4 times as much. It has 2 protons, 2 neutrons in the nucleus. Here you have the 4 protons. So it gets all of its energy from that. But these pieces that come out, particularly the electrons and the gamma rays, that's the energy that comes out. This has, in creating this, you actually release a lot of energy. Just like in burning, you release energy. When hydrogen burns with oxygen, comes together, it releases energy. When these 4 come together, they release a lot of energy. And it goes into the electrons, the gamma rays, and these mysterious particles called neutrinos, which we're going to be talking about more. These neutrinos, coming from the center of the sun, pass right through the sun and right through the Earth without us noticing it. In fact, some elaborate experiments have finally detected the neutrinos coming from the sun because these mysterious particles just pass through matter as if it didn't exist. But not the electrons and the gamma rays, so they give you the energy. Now, in ordinary fusion, like it's taking place in the sun, the reason the sun has fusion is because it is hot. The reason it's hot is because it has fusion. The center of the sun initially heated up just because of the gravitational collapse. The compression from all this enormous mass coming together heated up the sun enough that the velocity of the protons and the electrons that normally form a hydrogen atom, when it gets really hot, the electrons get knocked off. We have what we call plasma. So in the core of the sun, there are these free protons and these free electrons, and they're moving at very high speeds because it's hot originally from the compression of the gravity. These things are moving so fast that every now and then, the protons will come together and collide, even though they repel each other. Because they have so much energy, they overcome that repulsion. That high energy is the key to fusion. You get the heat, and that gives you the fusion. The heat gives them the kinetic energy to overcome the repulsion. That's why it's called thermonuclear. It's a thermonuclear reaction. If you get this energy by heat, it's called thermonuclear. If you get this energy not by heating something, but simply taking the protons and giving them a lot of energy and aiming them, then it's called cold fusion. Well, cold fusion, again, for example, occurs if you take a proton and put it in an electric field, make it go really fast. You accelerate it, but not by heat. Means for doing this, let's call it an accelerator. We'll talk more about it next week. If you accelerate the particle, and you can do this. I mean, we can't do it here. It's a little bit, but in the oil, people have oil wells where they make fusion. They send a little fusion device down. And what they do is accelerate the protons. Actually, they use deuterons, and they accelerate them, and they collide them because they're going so fast. They don't do it by heat. That's called cold fusion. Cold fusion is in the news a lot recently, and will continue to be in the news. They both use the same process. In this case, you just get it from heat. If you get it hot enough, then you get this rapid rate of fusion. That's what's done in the hydrogen bomb. In the hydrogen bomb, what you do is you have an atomic bomb that then heats up some hydrogen. They usually use deuterium and tritium, but those are just isotopes of hydrogen. And the heat of this ignites, that makes this so hot that this undergoes fusion. The exact details of that, some of them are discussed in the textbook. A lot of them used to be classified. Put a shell around this so that the heat stays in long enough to do this. And this combination is called the hydrogen bomb. And you can put more hydrogen in there and get a bigger explosion. So the biggest explosions are from hydrogen bombs. It's thermonuclear. Now, we'd like to be able to get this in smaller amounts than you get from a hydrogen bomb. A hydrogen bomb requires an atomic bomb, and an atomic bomb requires a critical mass. It's hard to make this thing small, but people are trying. And one way to make it small is with a pellet. Take a pellet. As I say, they have hydrogen in them, but the hydrogen is usually deuterium and tritium, two isotopes of hydrogen. They use this DT. This is really DT, deuterium and tritium. They use that because it requires a lower temperature. Now, what you do is when you have this hydrogen in this little pellet, just that big, size of your thumb, you hit it with lasers to heat it up. Or there are other things you can hit it with, things called particle beams. The idea is to have a little mini hydrogen bomb, just this big. And a little pellet that big will give off an energy of a million times more than you get from TNT. But gee, 1 gram of TNT, this becomes a million grams of TNT is like 1 ton of TNT. You could explode 1 ton of TNT with a little finger-sized thing at a time, put it in a big container, use the heat energy out to run a turbine. This is pellet fusion. Oops, P-E-L-L-E-T, fusion. This is one thing that it's still a serious, this isn't really cold fusion, but it's one of the possibilities. There's something in the news recently about cold fusion. People who are claiming that when they cavitate little bubbles, and then they collapse these bubbles, they get a flash of light coming out. Well, that's not too surprising. When you collapse a bubble, there's a lot of energy released. But they're also claiming to get neutrons out. And neutrons are one of the things that not part of that reaction. But in the DT reaction, you get a neutron coming out. And they claim they're seeing fusion. They're getting a few extra neutrons. This is in the news recently. And you may notice it when you see it, these claims of fusion. My own evaluation of these recent claims is that I'm willing to give you 10 to 1 odds that it's wrong. You put up $1, I'll put up $10. The only reason I'm not giving you 100 to 1 odds is I really want to make money. So personally, I feel they're 100 to 1, but I'm going to bet at 10 to 1. So I don't think that's going to hold up. But these are forms of cold fusion. Thermonuclear fusion, the kind that we really understand, there's an attempt to make that's been going on now since the 1950s. Now here's the problem. If you get things so hot that they're basically like the inside of the sun, you will get fusion. You will get more energy out, but how do you contain those? How do you put them in a bottle? It's so hot that it'll basically melt or vaporize any bottle that it's in. So the bottles they've come up with are magnetic fields. This is called controlled thermonuclear fusion. And one of the favorite, there are several different designs. The one that's received the most attention recently is something called a tokamak. I don't think I have this in the text. I'll have to add it in. But a tokamak takes a complex magnetic field and tries to store the deuterium and the tritium, DT, as a plasma, but having a strong magnetic field, these charged particles, if they tend to, by having the magnetic field lines go like this, the particles tend to spiral around the magnetic field lines, and they don't get out. And they don't actually touch anything except magnetism. So you put this whole thing in a big vacuum, use magnets to confine it, and you heat it up until it's hot enough to have fusion. That's the idea of the tokamak. Controlled thermonuclear fusion. Making conditions that are hot, like the interior of the sun, even hotter. using hydrogen gas, the two isotopes, deuterium and tritium, holding them in with a magnetic field. We'll show you more about magnetic fields next week. This is hot fusion, and it's what this is where billions of dollars are being spent to try to make tokamaks give us this source of energy.